Alright, we are going to get into topic 4. We're going to look at chemical formulae and chemical equations. So we'll start just review that every element has a specific symbol, atomic number, and mass number on the periodic table. Some of the elements have a symbol made of one letter and others of two. Make sure that you pay attention to capitalization. For example, here you have cobalt. Cobalt is C with a lowercase o, whereas capital C, capital O would be carbon monoxide, and these are two very different things. One is a metal element, and the other is a compound. So you can use this periodic table as we're working through these problems. Notice that it's been rounded and simplified just to make this concept a little bit easier to grasp without being so technical with the decimals. Now, a chemical formula shows the exact ratio of different elements that are present. The numbers of the element are shown with a subscript to the right of the element symbol. When only one atom is present, then we assume it's a 1, but we don't write it. So that would be, for example, C2H6. We have 2 carbons and 6 hydrogens. Or, for example, water, H2O, notice 2 hydrogens, only 1 oxygen, so we don't have to show it. Now, percent composition, it's a concept that we need to be familiar with. This is another way of referring to this is percent by mass or percent mass. All we're going to do is take the two masses, the mass of a component and the total mass, then multiply by 100, and we are going to get a fraction from it. So, say you had a 15-gram sample, and in the 15-gram sample you had 5 grams of oxygen in here. Okay, 5 grams of oxygen. What you would do is we could find out the percentage of oxygen in this sample by looking at it this way. We would see oxygen, the 5 grams, divided by your sample size, 15 grams, and then multiply that by 100. We'll see 5 over 15 is going to be 0.33 times 100 is equal to a 33% sample. Now, empirical formula is the simplest whole number ratio of atoms of each element within a compound. When you have mass data, that's where you can derive this empirical formula. So our method for doing this is we assume a 100-gram sample is present. We'll use the percentages, the percents by mass, assume a 100-gram sample. So, for example, if we were given a mass of, let's see, it was 20% element X, and it was 80% element Y by mass, we would then multiply these by 100, and we would see that this becomes 20 grams of X, and we would have 80 grams of Y. So that's the idea there. Now, we assume that 100-gram sample size, then find the smallest number we calculate in that size. Divide all the results of the calculations by that, that smallest number in 1, and this ends up giving us a molar ratio. Now, I will tell you, you should kind of caution yourself. Avoid rounding up or down too much. Be really lenient with sig figs until the end. Okay, basically do most of your rounding at the end. Always give it a padded digit or 2 right now. So once we have these results in 2, we should have these in a ratio that let us put it into an empirical formula. And that ratio, it could have a decimal. For instance, if we had 14 divided by 4, right? So if our ratio was 14 to 4, 4 being the small number that we divide, we would see that this ends up giving us 3.5, which is not a whole number. But a 0.5, that one's relatively easy to fix by just multiplying by 2. This will then become a 7. So, if we were given, it was 3.5 oxygens, and it was 5 hydrogens together, we would end up combining these and seeing that it's 7 oxygens with 10 hydrogens. Okay, so we'll get some more into that in a little bit. Now, Here we have another example that we're going to break down in a little more depth. We're already given the percent masses: 40.1% carbon, 6.6% hydrogen, and 53.3% oxygen. So we put this information together, and again, assuming a 100 gram sample, these percentages become grams: 40.1, 6.60, and 53.3. Then the molar mass values are put in: 12.011, 1.0079, and 16.00. What we'll do is we're going to take these masses, divide by the molar mass, and that gives us, so again, percent mass divide molar mass gives us our values here for number 1. What we're going to determine, we'll talk about this some more, but this is actually a value in moles of the substance. So now that we have the moles, you divide by the smallest. Notice that 3.34 and 3.33 are both smallest, and 6.55 divided by 3.33 is approximately 2. 3.34 divided by 3.33 is approximately 1, and 3.33 divided by 3.33 is 1. So our empirical formula could be written as C1H2O1 or CH2O. Alright, so here in task 4a, you're being asked to calculate the empirical formulae of the 3 oxides of iron shown below. What we can do, again on this, is use those steps that we'd addressed before. These, as percentages, need to be converted first to grams. Take the grams and divide by the molar mass, and then divide each of them by the smaller number in terms of moles. Once you do that, you should be given that whole number ratio. So I will let you work these out and show me that you're getting it on the online assignment. Second question: a hydrocarbon containing only hydrogen and carbon in this compound has percent masses shown here: 7.690 hydrogen and 92.31 carbon by mass. Then find its empirical formula. Okay, so again, I'll let you work this one out, and we'll talk about the molecular formulae now. So as opposed to the empirical formula, which is just the lowest whole number ratio, the molecular formula actually shows you what you have within the molecule in terms of a counted number of these things that are bound together. So again, it tells us exactly how many atoms of each element, exactly how many of each element are present. Okay, so the molecular formula is just a multiple. It is just a multiple of empirical formula. Where we had CH2O from before, if you multiply these all by 2, you get this C2H4O2, or by 3, it would be C3H6O3. Now, again, we're going to be using this molar mass. Okay, it's necessary to know the molar mass, or we also refer to this sometimes as the relative molecular mass, in order to find this molecular formula. Given that the molar mass is 60 grams per mole, it's clear that we would have C2H4O2. Okay, the way that this would be determined is, again, the empirical formula CH2O. That can be calculated as carbon is 12, hydrogen's 1, oxygen 16. So 12, 13, 14, and 16 is 30 grams in 1 mole of this empirical formula. The actual molar mass is 60, so that's a multiple of 2. So in doing that, we can see it's C2H4O2. Now, task 4b, go ahead and take the original compound from number 2, and we'll see if it was given this molar mass, this given 78.0 grams per mole, we would need to find the molecular formula of our compound. So, yeah, I'll let you guys go ahead and work this one again. It's a fairly straightforward procedure. You can ask for some help, either just email me or Facebook, whatever you need, and I'll be happy to help clarify this if need be. Now, chemical equations. Basically, these are just, again, a shorthand notation, a way that we can try to show what's going on in a chemical reaction. Okay, so shorthand is just an abbreviated method. Here's an example of a chemical equation. We have nitrogen gas and 3 hydrogen gas molecules. These are going to combine to form 2 ammonia gas molecules. So in order to write an equation, the first thing to do is go ahead and write the equation in words. The first thing that we would take again is, let's say we're given these components. We have sodium metal and chlorine gas. We combine these two things and we're going to make sodium chloride crystals. So the second step in our process is to substitute in the correct formula for all of these substances. So you essentially translate your words, take those words and put them into the symbol form. Also, you're going to add the plus sign to separate your species on each side and separate reactants and products with an arrow. So an example of this, remember we said it was sodium and chlorine. Sodium and chlorine combine to form, sodium chloride. The third thing is to balance our equation. Okay, so we're going to get into the specifics here. First, you need to just double check your work. Make sure that you have the right chemical formulae that are being used for our reactants and products. We do, in fact, taking a look here, we see that yes, this is the right way of showing sodium. A common mistake might be to just write Cl, but since chlorine is a diatomic, you have to have that in its Cl2 molecular form. Now we balance our equation. We're going to balance every element that we see in turn. Make sure that if you have anything in brackets that you multiply that out carefully. For example, BaOH2, if I'm counting all these things up, I'm going to see that I have 1 barium. However, because of the brackets, my oxygen number would be 2, and my hydrogen number would be 2 in that case. So, just as a planning, like a strategy thing for balancing, be aware that if you have an element that's only in one compound on one side, okay, so it's only in one compound and then it's alone on the other side, go ahead and balance that guy first if it's only in one compound. If it was in 2 compounds, like for example, if I had CO2 and H2O, notice oxygen is in both of these, then I would want to deal with that oxygen after dealing with one of these that's in only one compound. Okay. So then, if the reactants or product appear as a free element, so for example, I then have oxygen alone out here, you can balance the oxygen last. It's convenient, right? Because you have, you know, we might have some sort of a hydrocarbon over here, like C3H8, for example. So I've got CO2, H2O, oxygen, and C3H8. The next thing is go ahead and add your coefficients. Okay, you would place numbers in front of these formulae. These are again known as coefficients. Okay, I don't know why my pen is deciding not to recognize curves, but hey, these are coefficients. Be aware that the coefficients are going to be very, very important. A little bit later, we're going to be using coefficients to relate and convert from one chemical into another. So make sure that you don't change the formula, though. When you do this, the thing that you have to factor in is if you have NaCl, you can't add on another sodium. You can't just plug in a 2 there. If in the process of doing that, we would now make it a +2 and -1 in terms of our charge numbers, and that's not going to balance anymore. Remember, these things must equal 0. So Na plus and Cl minus come together, and they're going to equal a 0 charge overall. Okay. Now, so this shows us again, my Na plus Cl2 makes NaCl. Everything looks good here. Everything is fine. What we're going to want to do next is we're going to want to, again, incorporate coefficients based upon our balancing. Okay, so let's go ahead. Oh, I suppose I should probably do the actual balancing, shouldn't I? Do these things instead of just talking about them. So count these things below. Sodium, I have Na. There's only 1 sodium here. Chlorine, my Cl is 2. I draw a line here just to separate my reactants and products, kind of keep them straight in my head. And then on this side, I have a single sodium, Na is 1, and Cl is also equal to 1. So to balance this, I see that there are 2 of these. I would have to add my coefficient of 2. In the process, here I have Na will now equal 2, Cl will equal 2, and then I have to come back and check over here and see, oh, we're going to do a coefficient of 2 to give me 2, and now we have a balance. So we are now going to go ahead and add symbols for the state. S indicates solid, L for liquid, G for gas, and AQ indicates that we have an aqueous solution, right? A water-based solution. So going back to our original wording, we had sodium metal and chlorine gas will combine to form sodium chloride crystals. So what that tells us is a metal is in its room temperature state going to be a solid, so sodium metal, and then chlorine gas is given, so that's our gas state, makes sodium chloride crystals, and crystals, again, crystals are a solid form. So that wraps up the written chemical equation. Now, task 4C for you is to go ahead and write balanced chemical equations for the following reactions. We're going to do a little bit of translating here, and I'll work through one of these for you, and you can finish the other 2 up. So for A, I have hydrogen. Hydrogen, the symbol is H. It's diatomic, so it has to be H2. And this is combined with copper 2 oxide, so it's the copper 2 ion. The copper 2 plus would combine with oxygen, which is a 2 minus, in a 1-to-1 ratio, like so, CuO. This is going to combine to make copper, and copper being a metal in its simplest form is just a single copper atom. Combine this with water, which has the chemical formula H2O. So now that I have my H2 and my CuO combining to form copper and water, let's go ahead. I'll switch up my color here, make things clearer to break these apart. So I'm going to draw my line in. Now beneath the hydrogen, I see that there, the H, it will equal 2 here. Beneath copper 2 oxide, I have a single copper, and I have a single oxygen now. Beneath the copper on the product side, there's only 1, so I write that, and then I have 2 hydrogens, and I have a single oxygen. So looking left to right, I see that it's 2 hydrogens and 2 hydrogens. That one's good. I have 1 copper and 1 copper. That one's good. And then I have 1 oxygen and 1 oxygen. That one's good. So in terms of coefficients, this is already balanced. I don't have to worry about coefficients, right? These coefficients of 1 are already assumed. Okay? So it's 1 to 1 to 1 to 1 in terms of its ratio. So I'll let you solve the other 2 on your own, and then we can move on. So your last task, task 4C here, we're going to do some more balancing. So let me switch back into a different color here. Let's go to that guy. Now, in this case, I've got my calcium and water make hydrogen gas and calcium hydroxide. So this time around, let's go ahead and split this one. Calcium and H2O will react to form H2 gas and calcium OH2, calcium hydroxide. So we will do our split, do our count. Calcium is 1 here, hydrogen is 2 here, oxygen is 1, hydrogen is 2. Then over here we have calcium at a 1, oxygen is at a, notice in parentheses there's a 2 outside, so that must be a 2, and hydrogen is also a 2. So looking at my balance, I'm fine on calcium. Oh, am I fine on hydrogen? Look, hydrogen exists in more than one compound. So I'm going to write this out as H total, and I'm going to total these up from the 2 compounds. 2 and 2 adds for a total of 4. So let's see if we can fix that. Notice that I have 2 oxygens here, and I have 1 oxygen here. So a coefficient of 2 will effectively give me 4 hydrogens, 2 oxygens, and when I compare this now, everybody's balanced. So hopefully this makes some sense to you. If you have questions, again, feel free to post for me.